Hi everyone. So today we continue with chapter 7. In the last lecture we saw Gaussian processes, which was the first part of chapter 7. So today we continue with Bernoulli and Poisson processes. This is what we are going to see today. So let's begin with Bernoulli processes. So we have actually defined this process before in one of the previous lectures. So a Bernoulli process is a discrete time process that has independent and identically distributed samples. So each sample of a Bernoulli process can be seen as a random variable an, and these different random variables an's, they all have the Bernoulli distribution, so they are 1 with probability p, and they are 0 with probability 1 minus p, and each an is independent of the others. So we could maybe visualize a realization of a Bernoulli process. So it's a discrete time process, so it takes values for n equals 0, 1, 2, and so on. So each sample of the process is either 1 or 0. So let's just draw an example realization. So let's say that it's 1 here, and maybe in the next two samples it's going to be 0, then it might be 1 again, and 1 again, 0, 1, and so on. So a realization of a Bernoulli process looks like something like this. Here each random variable is called an. So an is the nth sample of the process. So each random variable an has a Bernoulli distribution with parameter p. P meaning that it is equal to 1 with probability p, and it's equal to 0 with probability 1 minus p. And the important thing to remember is that all these random variables a0, a1, a2, and so on, they are independent. So we can say that an's are independent, identically distributed. And we have seen before that such a process, a Bernoulli process, is stationary in the strict sense. So xn is SSS. So in fact, we have proved this before, but we could remember why this is the case. So this is actually quite like what we saw in the last lecture. We looked at the discrete time white noise process. So the idea is the same. Why are these processes strict and stationary? Just take some samples at some arbitrary time instance n1, n2, n3, and so on. So you're going to look at the joint distribution of those time samples. But since each sample is independent of the others, the joint distribution is simply given by the product of the marginal distributions. So it doesn't matter if you take your samples here or m moments later, so you're always going to get the same joint distribution. So this is why for processes whose samples are independent and identically distributed, we typically have the strict sense stationarity. Okay, so there is you can equivalently write down a Bernoulli process in terms of a convolution expression. So you could say that each sample is obtained by, well, the whole process is obtained by convolving these samples considered as a signal with the function delta n. So never mind about this if you find this confusing. So let's then think about the mean value and the autocorrelation function of the process. So we know that it's a strict sense stationary process, so the mean value should come out as something constant. So let's just confirm this. So let's find the mean function of the process, expectation of x of n for each nth sample. It means that we are looking at the expectation of each one of these random variables, so the expectation of an. But an is a Bernoulli random variable, 1 with probability p and 0 with probability 1 minus p. So let's find its expectation. So 1 with probability p plus 0 with probability 1 minus p. So it comes out as p. So the constant value p is the mean value of a Bernoulli process. So of course it doesn't have any dependence on the time variable n, because we know that it is a strict sense stationary. It has to be stationary in the mean. Alright, so there are also other ways of defining a Bernoulli process. So here, the most common example is, by the way, this one. It takes the values 0 or 1. But there are alternative forms for the Bernoulli process. So one might be Another common one is a Bernoulli process taking the values -1 and 1 instead of 0 and 1. So the definition is then almost the same. Each random variable in the nth for the nth sample takes the value 1 with probability p and takes the value -1 with probability 1 minus p. So you can similarly find the expected value of such a -1 Bernoulli process as p minus q, where q is equal to 1 minus p. So let's just maybe draw another realization for the -1 Bernoulli process. So the idea is the same. So we have a discrete time process. Each sample is equal to +1 or -1 with independently of the other samples. So a realization will look like something like this. Okay, takes the values either 1 or -1. All right. So now if we come to, well, maybe one thing to note about this is just imagine that p is equal to 1 over 2 here, meaning that the probability of having a 1 value or -1 value is the same. Then you can easily verify that this -1 Bernoulli process would be a zero mean process. It's quite simple to verify that. Now let's come back to our original 0-1 Bernoulli process and let's find the autocorrelation function of the original Bernoulli process. So our x of, well, we know that it is strict sense stationary, so our x of m is, we will obtain an expression in terms of m at the end of the day, but let's still write it as if we weren't sure about stationarity. So this is the expectation of the product x of n plus m, x of n. We are looking at the process at two different time samples, n plus m and n. So we know that each one of these is a random variable, so we are basically looking at the expectation of a n plus m times a n. And these are independent random variables. So we know that since these are independent, we can separate the expectation into two parts. But again, we should be careful here about the particular value of m, which is 0, which makes this independence fail. Because when m is equal to 0, you're looking at the same random variable an, and an is the same random variable. It's not independent. So we should consider this in two cases. So let's take care of the case m equals 0 first. So if m is equal to 0, it means that we're looking at the expectation of an square. It's the same random variable. But then the expectation of an square, remember, we are in the 0-1 Bernoulli case, so we're looking at this random process. So each sample is 1 with probability p. So if we look at the square of that random variable, it is going to be 1 with probability p, and it's going to be 0 with probability 1 minus p. So 1 times p plus 0 times 1 minus p. So we get p if m is equal to 0. And otherwise, for other m values, we have two different and independent random variables. So we get the expectation as the product of the expectation. So expectation of a n plus m times expectation of a n. And we just showed that for the 0-1 Bernoulli process, the expectation of each value is equal to p. So we can now use it here. So this expectation is equal to p. And the other expectation is also equal to p. So p times p, we get p squared for other m values otherwise. Okay, so we could just wrap it all together to write an expression for the autocorrelation function of the 0-1 Bernoulli process. So we see that it all depends on m, the time difference. So we could just omit the notation n here. So our x of m, so let's write this down as a function of m. So we see that there's this common constant value p squared everywhere. So let's write p squared. And then we have to take care of the particular case m equals 0. So since this holds only for m equals 0, it means that we are going to put an impulse at m. And then to make the value equal to p at m equals 0, we have to subtract this. So if we put p minus p squared times delta m, then it's going to do the job. Okay, so this is the autocorrelation function of the 0-1 Bernoulli process. So we just verified that it's stationary in the mean, and next it's stationary in the ACF because the ACF depends only on m, the time difference. But this was an expected result because the process, we know that it's strict sense stationary, so of course it's going to be wide sense stationary. Okay, now back to the case, the -1-1 Bernoulli process. So back to this case. So you can similarly look at the mean value and the autocorrelation function of the -1-1 Bernoulli process. The derivation is exactly the same. If you can do this as an exercise, take this process and then follow similar steps as we did in here. You can obtain the autocorrelation function as this expression. I leave it as an exercise to you. So that's easy to do, but in fact there's a funnier way of doing it. So this -1-1 Bernoulli process, so this one can be obtained directly from the 0-1 Bernoulli process. Just imagine that somebody gives you a 0-1 Bernoulli process, x of n. So imagine you're multiplying this process by 2, so the values are either 0 or 2, changes between 0 and 2, and then shifted by 1 down. So the values are going to be between -1 and 1. So what you have done is you have taken twice the 0-1 Bernoulli process, multiplied by 2, and then shifted downwards by 1. So this gives you the -1-1 Bernoulli process. So you could just verify using the expression for the, this one, the one we just found, the expression for the autocorrelation function of the 0-1 Bernoulli process. You can just use this relation, y equals 2x minus 1, and you can obtain the autocorrelation function of y in terms of the autocorrelation function of x, and then plugging in the expression we just derived, you can verify that the ACF of the -1-1 Bernoulli process is given by this expression. Okay, now the -1-1 Bernoulli process has an interesting property. So if you just, if you take p is equal to 1/2, now going back to the expressions, I guess this one, if p is equal to 1/2, then this term is going to disappear, and this term is going to come out as 1. So you then get the ACF of the random process as equal to delta m. So when p is equal to 1/2, the ACF of this, let's call this as x now for simplicity. So the -1-1 Bernoulli process with parameter p is equal to 1/2 has the autocorrelation function as equal to delta m. So the ACF is just an impulse at m equals 0. It's 0 everywhere else. And now if you consider the power spectral density of this process, so let's find as x of e to the j omega. So it means we are taking the dTFT of the autocorrelation function, but the dTFT of the impulse is the constant value. So it's an impulse of strength 1. So we get a power spectral density that's constant everywhere, that takes the value 1 everywhere for any discrete time frequency omega. Now, if you remember the definition of discrete time white noise processes, we define it as a process that has the autocovariance function as equal to an impulse. So since this process is zero mean, when p is equal to 1/2, the expectation of the process is going to be obviously 0. So this is a zero mean process, meaning that the ACF and the autocovariance function are the same. So this is in fact a white noise process, a process that you obtain in this way. Well, actually, maybe you could even intuitively immediately say that this is a white noise process of zero. I mean, mean is 0 and the samples are independent. So whenever you have independence, so of course you have uncorrelatedness. So along with zero mean, this is the autocovariance function you get, and the PST is going to be flat. So this is a zero mean white noise process. So just another, let's also remember that there is not a single way of constructing a white noise process for the discrete case as well as the continuous time case. As long as the spectrum is flat and the samples are uncorrelated, then you get a white noise process. The samples individually, if you look at the distribution of each sample, you could have a few alternatives. In this case, it's a Bernoulli distribution. In some other cases, it could be a Gaussian distribution, like we saw in the last lecture, I guess. It was discrete time white noise Gaussian process. So there's not a single way of generating white noise, so this is just one of the examples. Okay. Now back to the 0-1 Bernoulli process. This one, you could then wonder, let's say that we had the value 1 here. And then we look at the other values. So what is the typical amount of time that I have to wait until I get the next one value? So it's stated formally in here. So the distribution of the time interval between successive non-zero values of x of n. So what is this probability distribution? Okay, let's think about this question. So let's just draw another realization of the 0-1 Bernoulli process. So let's say that the process started at, well, it doesn't have to start at n equals 0. You could have other n values. Anyway, so you have some samples. So we don't mind what's happening here. Let's say that we are looking at the process at some arbitrary n value, and then we happen to have some have the 1 value. It's some n value, and then we're wondering when is the next time that the process is going to have the value 1 instead of 0. So each sample is independent of the other, so you could immediately get another 1 value in here, in which case the time interval would be 1. Or maybe you could have 0 here, and then the next case you could have gotten 1. In this case, the amount of time that you have to wait between these two 1 values would be 2. So we're wondering about the probability distribution of this. So let's just try to find the probability that the amount of time that we have to wait until the next 1 value is equal to k. So this is going to be denoted as the random variable n. So the random variable n is the amount of time that we have to wait until you get the next 1 value. So what is the probability that n is equal to k? So n is equal to k means that you got 0 in the next k minus 1 trials, and then finally at the kth trial after this value you finally manage to get 1. So it goes at 0, 0, 0 everywhere, and then at the value n plus k you got 1 again. So what is the probability of this? Let's find this. So the probability that n is equal to k, so for this to occur, first of all, the next one should be 0, otherwise n would be equal to 1. So, but having the 0 value in the next one has probability 1 minus p, right? And then the next one should also be 0, so 1 minus p again. So actually the next k minus 1 value should be 1 minus p. And then finally at the kth trial you got 1, which has probability p. But then you have k minus 1 of these, so this gives you 1 minus p to the power k minus 1 times p. So this is the probability distribution of the amount of time that passes between two successive 1 values of the process. Now, if you think about the name of such a distribution, maybe some of you remember, this is called the geometric distribution. So this is a discrete random variable that's called the geometric random variable. I guess we were drawing quite often the probability mass functions of such discrete time random variables in the EE 230 course. But now here we don't use PMF in this course, so we state distributions in terms of the PDF. So you could write down the PDF of the geometrically distributed random variable in terms of impulses, if you allow yourself to use impulses when writing down PDFs. So the PDF would be the following. So since let's think about what k values we might obtain. What are the possible values that this random variable takes? So we are counting in time, right? We are counting trials, first trial, second trial, and so on. So k might be 1, k might be 2, so it could be any positive integer. So that means that we have a summation over all possible k values from 1 up to infinity, and we have an impulse for each k value. And the strength of that impulse is going to be the probability of having that k value for your random variable. So you might even draw the PDF of the geometric random variable. So since we are talking PDF here, so we should use a continuous time variable x. So x can take the value of 1, it can take the value, I'm sorry, n. The random variable n can take the value 1, 2, 3, 4, and so on. And since you have countably many values, you have impulses. So the first one has probability p, the second one would have probability 1 minus p. The third one would be 1 minus p squared times p, and so on. So this is the probability density function of the random variable, geometric random variable n. So it's a discrete time random variable, so it's a discrete random variable, so you have impulses in the PDF. Okay, so this is about the Bernoulli processes. Now, the next process that we're going to look at today is the Poisson process. So the Poisson process is something quite interesting. So it's usually used for counting or modeling the number of arrivals to some place. So we had given some examples in the previous lectures. So you might be interested in modeling the number of customers arriving at a store, or modeling the number of I don't know, photons hitting a sensor and things like that. So it's about the arrivals, but the word arrival is used figuratively here, so it could be in fact anything, but we'll just use the terminology arrival to talk about these discrete events occurring somewhere at some random time instance over time. Okay, now we will define it formally, but I would just like to give you some intuition about in what kind of situations we can use Poisson processes to model our problem. So you should have a situation where the different arrivals should be independent of each other. So it means that I'm running a store, I have customers arriving. The fact that I have a customer right now should not change the probability of having a customer 1 hour or 2 hours later, because each customer arrives independently of the others. You're in a situation like this. So you can model arrivals as things that occur independently of each other. So another assumption we make about Poisson processes is that the average arrival rate is constant, doesn't change over time. So I'm running a store again. I know that in the average I have 3 clients per hour. So it's going to be 3 clients per hour in the morning, it's going to be the same in the evening, and so on. And the last thing we assume, this is for technical reasons, we assume that 2 arrivals cannot occur at the same time. But I guess this is quite reasonable because you have a continuous timeline t here, it's a continuous thing. It's very, very little probable to have 2 people arriving exactly at the same time moment, just thinking of this as a real number. So this is usually quite okay. So there's a comment here that tells you that Poisson processes are related to the Bernoulli processes in some manner. Careful here, Bernoulli processes are discrete time processes. So we draw x of n, like n equals 0, 1, 2, and so on. Poisson processes will be continuous time processes. We're going to have a constant, a continuous time variable t for studying Poisson processes. But a Poisson process can be seen as a limit of a Bernoulli process, or can be seen as the continuous time counterpart of a Bernoulli process. So we will keep that for later, but just a little note to tell you that these 2 processes are quite related. Okay, so after all these things, so let's maybe get started with the Poisson process. So I'll just begin by drawing a realization of a Poisson process. So what kind of things are we going to be dealing with? So there are two forms of the Poisson process that we are going to study. So what I draw here will be called the Poisson counting process. So we are counting the number of arrivals. Okay, so this is the timeline T. So arrivals will, well, a Poisson process almost always starts at time t equals 0 because you have to give it a beginning. So the process starts at 0, and then we have arrivals occurring after the time instant 0. So maybe the first arrival will occur here. Of course, they occur randomly. They are not evenly distributed or anything like that. They arrive, people arrive randomly at my store, something like that. So maybe another one will occur here. So I'm counting how many arrivals I have obtained so far. So between 0 and T1 until this moment, I had no arrivals. And then at T1, one person arrived, so I got 1. So the value of my process increased to 1. And then at T2, another person arrived, so I got 2. And so it goes on and on like that. Maybe some third person arrived in here. T3. So the total number of arrivals became 3. So then it goes on like this. So it's some T4, it's some T5, and so on. So, okay. This is going to be 4 here, and this is going to be 5 here, and so on. So this is a Poisson counting process. So now, well, there are actually 2 different versions of the Poisson process we are going to deal with. We will first look at what we call the Poisson counting process, which is going to be this one. And then we will define something called the Poisson impulse process, which is basically going to be the derivative of this one. So we are going to have impulses each time a new arrival occurs. So we will first begin with the first one. All right, now up to now, we haven't given a formal description of a Poisson process. We have just looked at some intuition behind it. Let's now formally define a Poisson process. So the thing is, well, how do you model such arrivals, or how do you model the people that have arrived in a given time interval? Let's begin by that. Well, you all know the Poisson random variable, so you might suspect that this new thing called the Poisson process should be related to the Poisson random variable in some way. Well, this intuition is correct. What will happen is the following. So, how is the Poisson random variable coming into play here? So let's now imagine that we are looking at the process at some time instant, arbitrary time instant t1. I will call it as small t1, not to confuse with the capital T's that we will use for denoting the arrival times. These are random variables. This is just a dummy real variable meaning a time instant. So let's look at some t1, and then let's look at some t2. Let me take a t2 in here. So these are just arbitrary time instants. I can take them anywhere. So then what I'm looking at is the number of people that arrived between t1 and t2. So I could just write it down on my drawing. So the number of people that arrived between at the moment t1, I still have 1 person. At the moment t2, I have 3 people that arrived. So the number of people that arrived between t1 and t2 is actually going to be a random variable, right? Well, in this realization, example realization I drew, it happened to be 2 people, but then since the arrival times are random variables, in another realization it could be 3, it could be no arrival. So this is a random variable. So let's give a name to that random variable. So I will call it n of t1, t2. Meaning, this means that number of people that arrived between a time instant t1 and a time instant t2. Now, I could look at it at some other time instance as well. So if I take some t3 in here, I will similarly get the random variable, that's the amount of people arrived between the time instant t2 and t0. So my notation will be the same, n of t2 and t3. Now, why did we define all this terminology? Well, the way we define a Poisson process is the following. There are two properties that are important. The first one is that whatever t1 and t2 I choose, when I look at the number of arrivals within the interval t1, t2, this random variable has to be a Poisson random variable. We'll define it more formally, but n of t1, t2 is a Poisson random variable. And similarly, of course, if I change t2 and t3, this one should also be a Poisson random variable. So in whatever time interval I take, could be here, could be here. If I look at the amount of people that arrived within that time interval, it has to be a Poisson random variable. This is the first property that a Poisson random process should have. And a second property, an important property, is that the arrivals in disjoint time intervals, like in here, so if I look at n of t1, t2, the arrivals between t1 and t2, if I look at n of t2, t3, is another random variable, arrivals in this interval, these two random variables, which are both Poisson distributed, they should be independent because the time intervals are disjoint, they are non-overlapping time intervals. So t1, t2 is here, t2, t3 is here, they don't overlap, so the arrivals here and here, they should be independent. So these two properties is what formally defines a Poisson random process. Now we will do that formal definition, but for those of you who don't remember the Poisson random variable, let's first remember that briefly. So I'll call it n in here to make the link. So now we have forgotten about random processes, we're just in the random variable case here. So n is a random variable. So if it's the Poisson distributed random variable, it should have some parameter mu, then its distribution is the following. So the probability that the random variable takes the value k should be this one. This expression is parameterized by mu, and of course it depends on k. So again, what can k be? K can be 0, 1, 2. So if somebody talks to you about a Poisson random variable, a Poisson random variable is typically about the number of arrivals, just like in our context. You might have 0 arrivals, or you might have 1 arrival, 2 arrivals, and so on. So it takes non-negative integer values. And the probability of 0 arrival would be obtained by putting k equals 0 here. Probability of 1 arrival would be k equals 1, and so on. And the whole expression is determined by some parameter mu. Now, if you try to draw this as a function of k, typically it first rises up for increasing values of k, and it makes a peak somewhere around k equals mu, and then it falls back again. So we studied the Poisson distribution, I guess, in the beginning of the semester. So it's possible to derive the expected value, the variance, and some other properties. So you can verify that if n is a Poisson random variable with parameter mu, its expectation is mu, its variance is also equal to mu, and similarly you can find the expectation of n squared from the variance expression. It comes out as mu plus mu squared. So this was a brief note about the Poisson random variable. Now back to the Poisson process, Poisson random process, we said that let's now define it. So a Poisson counting process, we're defining the counting process version. So a Poisson counting process is a process such that the number of arrivals n of t1, t2, just notice that this can be written as x of t2 minus x of t1, while x of t is the total number of arrivals. Of course, this is going to be x of t2 minus x of t1. So this random variable, number of arrivals between t1 and t2, within any time interval t1, t2, should be a Poisson distributed random variable. With which parameter? Again, if you talk about a Poisson random variable, you have to specify its parameter mu. The mu here should be equal to lambda times t2 minus t1. Of course, it depends on something called lambda. Actually, lambda is going to be called the rate or the parameter of the whole process, the Poisson process. So it's going to determine how often you have arrivals. And of course, the number of arrivals between T1 and T2, it should depend on the time instance, T1 and T2. So it's a Poisson distributed random variable with parameter this, lambda times T2 minus T1. Okay, so this is the first property. And the second property that a Poisson process should have is that the number of arrivals in non-overlapping intervals, so disjoint intervals, should be independent. So n of 0 T1, n of T1 T2, n of T2 T3, all of these should be independent random variables. These are all Poisson distributed random variables, but they are independent random variables, telling you it's actually quite aligned with the spirit of Poisson processes that different arrivals are independent of each other. So this process and that, this random variable and that random variable, they are all independent of each other. So let's maybe just note down on our picture that these random processes, these random variables, so this one and that one, these are Poisson distributed. So these are Poisson random variables, and these are independent because the time intervals are disjoint, they are non-overlapping. Okay, so this is the definition of a Poisson process. Now, you could also deduce the distribution of the process x of t itself. Why? Because x of t, you can also write it down in terms of the n terminology. So x of t is nothing but the number of arrivals between 0 and t, right? This is how we define the counting process. So this is the number of arrivals between 0 and t, so it's equal to n of 0t. But remember, n of t1, t2 is Poisson distributed, so n of 0t must also be Poisson distributed. And with which parameter? So remember, it comes from the definition of the Poisson process. If the number of arrivals between T1 and T2 has parameter lambda times T2 minus T1, well, here T2 must be this and T1 is 0, so the parameter is lambda T, right? Okay, now, first of all, let's give some meaning to this. What is the role of lambda in the whole story? So when somebody gives you a Poisson process, they will always specify what this number lambda is. It's a known constant that's called the rate of the process. Now, why is it called the rate of the process? Let's think about it again. So let's focus on x of t. X of t is, I'm taking some arbitrary time instant t, and I'm looking at how many arrivals I obtained up to that time instant. That's a Poisson random variable. It has parameter lambda t, but the parameter lambda t, let's relate it to the actual number of arrivals that we would expect to have between the time interval 0t, right? So remember the property of the Poisson random variable. So the expected value of a Poisson random variable is mu, where mu is the parameter. Here our parameter is lambda t, so the expected number of arrivals, so the expected value of x of t, since this is a Poisson random variable, must be lambda times t for any t. Now, what does this physically mean? It means the following: it totally makes sense to call lambda the rate of the process. Why? Because when lambda is high, it means that I'm expecting a higher number of arrivals. So if I run a store, I would like to have a large lambda to have a lot of customers, because I'm expecting to have lambda t customers per t unit. So if t is equal to 1, it means that I'm looking at the customers that were arrived between 0 and 1, so it's going to be lambda. Lambda is higher, the arrival rate of customers is higher, so I expect to have more customers. So lambda is the parameter that specifies how often you will have arrivals at a Poisson process. It's always specified when somebody gives a Poisson process to you to model a problem. Okay, now this is the definition of a Poisson process. You also see a sample function, a realization of the process plotted in here. So these are the random arrival instance, T1, T2, T3. Again, don't forget that these are random variables. In a certain realization, the arrivals might occur here. In another realization, I might have no arrivals up to here, and I might have the first one in here. So these are random. And then you can also notice that this goes as a staircase. Any realization of a Poisson process goes like a staircase function. So you could write it in terms of the sum of some unit step functions. The first one starting at T1. So you're adding the second one starting at T2. It goes on and on like that. So now we might ask the following question. So we have understood it so far. What characterizes a Poisson process? It's the fact that the number of arrivals in any time interval is a Poisson random variable. Now, if I ask you the following question, now, if I'm interested in how much should I wait between two arrivals, so let's say I'm waiting for customers, the first one arrived, the second one arrived here, and I'm wondering when the third one will arrive. So I'm wondering how much I should wait until the third customer, the next customer arrives. So this is about the inter-arrival times of the Poisson process. So let's maybe draw another picture to represent that. So let's take a Poisson process x of t. I'll just maybe shift it a little bit. Okay. So I have a Poisson process. I'm just again drawing a realization of my process. So it starts at t equals 0. So this is the t timeline. So the first arrival occurred here. This is a random variable. And the second one occurred here. Maybe the third one might occur here, and so on. And I would like to know what's the amount of time that I should wait between consecutive arrivals. So I will give another name to this. So let me call this first one as x1, the first inter-arrival time that passes between 0 and the first arrival. And the second inter-arrival time, let me call it x2. And the third one would be x3, and so on. Now, it's not immediate to... maybe at this point you might think about what is a valid question to ask. You know, can I find out what kind of distribution? I'm thinking about the distribution of these random variables. What must be this distribution? So what I know so far is the fact that it's about the distribution of the number of arrivals in a given certain time interval. So this is Poisson distributed. I know the rate and the parameter and so on. But then what is the distribution of the waiting time between two arrivals? Now, first of all, notice that it's not the same distribution. First of all, this is a discrete random process. It takes values like 1, 2, 3, and so on. But this is a continuous, random variable. This is a continuous random variable, so it could be any real number. Well, I'll give you the answer. It turns out that for a Poisson process that's defined in this way, where the number of arrivals within each time interval is a Poisson random variable, you can do the maths and you can find out what this distribution is. We won't do it, but I'll just give you the answer. The inter-arrival times in a Poisson process are exponential random variables. It turns out to be that way. So the inter-arrival time x between consecutive Poisson arrivals is an exponential distributed random variable with this PDF. So this exponential PDF, I could just maybe draw it here. So it's called x in the definition, but in fact, each one of these random variables, x1, x2, x3, they are all exponential random variables that have the following PDF, the exponential PDF. So starts at 0, takes the value lambda at x equals 0, and then decays exponentially in time. So this is not the only deduction. The next thing is that the different inter-arrival times, x1, x2, x3, and so on, they are all independent. So this means that x1 and x2 and x3, they all have the same distribution. They have this distribution. They're all exponential random variables, but they're independent of each other. So This might be a little bit confusing. What is the definition of a Poisson process? In fact, there are two ways of defining a Poisson process. The one we did here is we defined it based on the number of arrivals in a given time interval. Now, if you accept this as a definition, it's possible to prove that the inter-arrival times should have an exponential density. And in some other alternative definitions of the Poisson process that you might see in some books, they go the other way around. They say that the inter-arrival times are exponentially distributed and independent of each other, in which case you can show this to prove that the number of arrivals within a given time interval should be a Poisson random variable. So you can either define it this way and prove the other, or do it the other way around. So these are all alternative ways of defining the same process. It's interesting. It's not very easy to prove, well, assuming that this is a Poisson random variable, it's not very easy to prove that this is an exponential random variable, but what you can do is you can take infinitesimal time intervals, and then you could look at the probability of having an arrival there, and then you do the Taylor expansion and so on. So to switch between one definition, to take one definition and pass to the other one. But never mind, we don't have to do it. Just know that these are the properties of a Poisson process. All right. Now, again, one thing that's important here is remember the property of the exponential distribution. So if a random variable has the exponential density given like this, its expected value is equal to 1 over lambda. So the expected value is equal to 1 over lambda. Well, you can also see this as, well, if you take a small lambda value, the density is like this. Now, if you take a higher lambda value, let's call it as large lambda. This lambda is higher in this case. But lambda getting higher means that the density is squeezed to a portion of the real line that's closer to 0, in which case the expected value will obviously decrease. So this is in line with the result that the expected value of an exponential random variable should be inversely proportional to lambda. So in fact, if you just do the calculation, you'll see that it's 1 over lambda. Now, why does it make sense within the context of a Poisson process? I'll just draw a realization of a process in here. So the first arrival, the second arrival, the third arrival, and so on. So well, this is a Poisson process, a typical realization that you might obtain for a certain lambda, right? Somebody gave me a lambda, and this is a typical realization it might produce. Now, let's also relate what we saw so far. So the number here is going to be x of t, which is n of 0t, an equivalent way of writing this. We just saw that this is Poisson distributed. This random variable is a Poisson random variable. And we just saw that its mean is lambda t. And then now, going back to these, the inter-arrival times are exponential random variables. So all these random variables, x1, x2, x3, I'll just maybe denote them here. All of these random variables, they are all exponential distributed. And they are independent of each other. And their mean is equal to 1 over lambda. The mean of each one is equal to 1 over lambda. Now, what happens to my process if lambda increases? Meaning that I have a Poisson process occurring at a higher rate, having a higher rate. When lambda increases, the number of arrivals that I have up to some certain time instant, let me just mark a time instant in here, some t here, let's say. The number of arrivals that I obtain between 0 and t has expectation lambda t. So when lambda increases, I'm expecting to have a larger number of arrivals. On the other hand, the amount of time that I have to wait between two arrivals here or here is equal to 1 over lambda, so it goes down with lambda. As lambda increases, the inter-arrival time goes down, it decreases, which totally makes sense because I have arrivals that are more frequent, so I have to wait a less amount of time between two arrivals. These are all coherent with each other, in fact. Alright, so this is the well, what we saw up to here is really basics of a Poisson process. Now you know the most important, the most significant part up to here, as far as the definition of a Poisson random process is concerned. So now the next thing we might wonder is the statistics of the Poisson process. Let's now switch to go back to our random process x of t. Now, can we talk about the first order density of the random process? Of course, we can talk about, but what is it? And then what is the mean function of this random process? And can we find out the autocorrelation or the autocovariance function of the random process, and so on. Now, first of all, the first order density is quite straightforward. Why? For each t, x of t is a Poisson random variable with parameter lambda t. The mean is equal to the parameter. So the first order PDF of the Poisson counting process is the Poisson density, right? The Poisson distributed with parameter lambda t. So, of course, this is a discrete random variable, so it takes the values, integer values like 0, 1, 2, and so on, because it's the number of arrivals. But if you would like to model this with a continuous PDF, a density function, you can still do it if you use impulses. So the values that x can take are integer values, so you have impulses at k, and here is the probability. So here is the probability of each k. So if you just plug in k equals 1 in the expression, that's going to be the probability that you have 1 arrival, similar for k equals 2, and so on. So you could in fact even plot this density. So I guess this is the way we write it now. The first order density function of the Poisson counting process evaluated at some time instant t. It's a discrete, this thing is a discrete random variable, so it has impulses in this PDF. So you might have 0 arrivals, or maybe you will have 1 arrival, and then so it typically increases up to some point, and then it will start decreasing for larger x values. And impulses are always located at integer values of x. And typically the peak here, well, let's say, the peak here occurs at some x value close to lambda t, because lambda t is the mean, the parameter of this Poisson random process. So this is Poisson distribution. Poisson distribution with parameter. I'll just write mu again. Mu is equal to lambda t. Okay. Now, the first order density is fine. Well, what about the mean function? Obviously, the mean function is going to be equal to lambda t, because it's the mean of at each t value. Now, we can also maybe write it down. The expectation of x of t, the mean function is equal to lambda t. The variance function is also equal to lambda t, because it comes from the property of the Poisson distribution. Remember, a Poisson random variable, where was it? A Poisson random variable has expectation equal to mu, variance is equal to mu, and so on. So now if I ask you about the stationarity of the Poisson random process, so is this random process stationary? The first thing you might check is stationarity in the mean. So it's not even stationary in the mean. If you drop the mean function of the process, it increases linearly with t, right? So there's no way this process could be stationary. So still, let's find the autocorrelation function of the Poisson counting process. So here you have the expression turns out to have this rather ugly form. So let's drive it. So Rx of t1, t2, we are looking at the expected value of x of t1, we are looking at process some t1, and x of t2. Now you could write x of t1 as equal to the number of arrivals between 0 and t1, so similar for x of t2. Now if these are independent and you can do the separation, then life is easier, but we are not allowed to do that now. Why? Because these intervals are not disjoint. So 0 t1 overlaps with the interval 0 t2. So the trick would be to make them independent by just breaking the second interval into two parts. So if I write down instead of this, if I write down the expectation, this one, I keep the first one, but then I look at the number of variables between T1 and T2. Now, this first interval is disjoint. It's non-overlapping with the second interval. So from the definition of the Poisson process, I know that the number of arrivals here and here, they should be independent of each other. So I can separate this expectation into two parts. So I can write it as this. Now the rest is going to be just mechanical. So, all right, let's now just develop this. We'll work out both sides of the equality. So this one is going to be, this term is x of t1. So I write it here. The second term is equal to xt2 minus xt1. So we write it here. Now we keep the equality, and on the right-hand side, this is the expectation of x of t1, and the second expression is going to be expectation of xt2 minus xt1, number of arrivals between t1 and t2, so we can write it this way. So, so it's just arithmetic, so just distribute this onto both terms, so you have the first term, x of t1, x of t2, minus, here we have x of t1, multiplied with the self. So expectation of x squared t1. And in this side, you could just use the properties of the Poisson random variable. So this is a Poisson random variable with parameter lambda t1. So its expectation is lambda t1. And then this is a Poisson, well, it may be easier to see from here. This is a Poisson random variable with parameter lambda times t2 minus t1. So here is its expectation. Now, going back to this side, what we recognize in here is the autocorrelation function of the Poisson random process, so Rx of T1, T2. Now, this part, you can similarly remember that this random variable x of T1 is a Poisson random variable. We know its mean, we know its variance. From the mean and variance, you can write down the expectation of the square of that random variable. It's basically going to be the variance plus the mean to the power 2, so you can write it this way. And then still working here, you distribute the expressions, and then you realize that this term cancels with that term, and then finally you get the autocorrelation function as equal to lambda 2 t1 t2 plus this term. So this is the first part of the autocorrelation function. Here, just be careful, we have used the assumption that T1 must be smaller than T2. Where did we use it? We use it when breaking this interval into two parts, so the order has to be respected. Now, if you just think about the other case separately, what if T2 is smaller than T1? It's exactly the same derivation, it's just that the rows of T1 and T2 are switched. You just rewrite the same equations with the opposite order of T1 and T2, you get the same expression due to the symmetry. It's just you plug in T2 instead of T1 and so on. So you get this expression. Okay, so you have this rather inconvenient form for the autocorrelation function. So what's important, I mean, don't try to memorize this, or you don't have to know this by heart, obviously. So, but what you have to notice here is that this function is not, it's not the ACF of a stationary random process. Why? If for the Poisson process to be stationary in the ACF, this should come out as a function of T1 minus T2, which is not the case, so we know that the Poisson random process is not stationary in the ACF. Okay, now, okay, the effort then in the rest of this chapter is today's lecture is going to be to make the Poisson counting process. So take this process and convert it into a stationary process. Well, let's maybe think about what we are trying to do peacefully. Now, this process is obviously not stationary because the number of arrivals that you obtain, of course, increases in time. So it's a monotonically increasing. Any realization is increasing. It's an increasing function of this. So there's no way it should be stationary. Why is this the situation? It's basically because of the fact that we are counting the arrivals from 0 up to the time instant where we are. Of course, it's going to increase with time. But in fact, when you think about the very nature of the Poisson process, it's all about independent arrivals, right? well, the probability of having an arrival here is the same as the probability of having an arrival at another disjoint time interval. So there is some kind of independence in the nature of this process. So how can we take this Poisson process and put it in a form where you could, in fact, conclude some kind of stationarity? This is thinking intuitively, this should be possible to do. So the trick would be the following. We shouldn't count to achieve stationarity, we shouldn't count the number of arrivals from 0 on, but we should kind of look at it momentarily. So if I just focus on each time instant t, if I look at whether I have an arrival or not at that time instant t, then that process, that form of the Poisson process is going to have this stationarity property. Of course, it's going to be something weird. It's going to consist of impulses and so on. But if you think about it, this thing is kind of related to the Bernoulli process. Just think that you have all this constant, the continuous timeline t. So t is a real number. And imagine that you're interested whether you have an arrival occurring at t or not. First, notice that arrivals occur at countably many time instances, right? One arrival here, another arrival here, and so on. So you can maybe first ask, what is the probability of an arrival at a given? If I take some t here, what is the probability that an arrival will occur at that exact time instant t? It's obviously 0 because there are uncountably infinitely many time instances here, and only finitely many of them have an arrival in practice. So the probability of an arrival is 0. But then, if you relax this a little bit, if you don't just take some t, but if you take an infinitesimal delta interval around a time instant t, then you're wondering whether a arrival occurs between 0 delta, delta 2 delta, 2 delta, 3 delta, and all of these intervals. You could model this as the limit of a Bernoulli process, because the Bernoulli process would be telling you that the probability of an arrival is p in the first infinitesimal time interval, and arrival with probability p in the second time interval, independent of the first time interval, and so on. So in the limit, when you take delta approaching 0, you get the Poisson process from the Bernoulli process. This is in fact a nice exercise. You could if you're a maths person, you could just think about obtaining the Poisson process as the limit of a Bernoulli process. The only thing you have to do is relate that probability of arrival in each infinitesimal time interval, so p, to the parameter lambda of the process. So you should be finding a relation between p, delta, and lambda. But I mean, if you're not that interested, never mind. You don't have to do that. Now, all this was to tell you that we know that the Bernoulli process is strict sense stationary. We saw it. It has a stationarity property. So if we take the Poisson random process and if we put it in this alternative form where we focus only on the time instant, actual time instant, not the arrival so far, but whether there's an arrival or not at that particular time instant, we'll get a stationary process. So let's now do the maths of this. So this is what we call the Poisson impulse process. Very simply, it's going to be defined as the derivative of the Poisson counting process. So take x of t, differentiated with respect to t. Of course, you have this discontinuity, so you're going to get a delta here, and an impulse, and another impulse at t2, and so on. So it's going to consist of, you can formally show it as, if you write x of t in terms of unit step functions, you differentiate it so you get deltas. So let's just draw a realization of the Poisson impulse process. So let's begin with our usual Poisson counting process, x of t. I'll just draw a realization of x of t first. Starts at 0. Let's say the first arrival is at some t1, and the second arrival at some t2, and a third arrival here, so it goes 0, 1, 2, 3, and so on. Now, if you take the derivative of that process, z of t is equal to d by dt x of t. the derivative of this process would consist of impulses. So the first impulse would be at t1, the second impulse would be at t2, the third impulse would be at t3, and so on. So an impulse here, impulse here, impulse here. So what should be the strength of the impulses? So the strength of the impulse should be proportional to the amount of jump, but the jump is 1, so they all have strength 1. They each correspond to a single arrival. Okay, so again, these are both Poisson. These are both some ways of representing a Poisson process. They actually refer to the same process, but this version is called the Poisson counting process, whereas this one is called the Poisson impulse process. The first one is not stationary. Now we will just show that the second one is stationary. So let's do that. So let's first stationarity in the mean. So the mean value of the Poisson impulse process is equal to lambda. Let's prove it. So that since it's not time dependent, it's stationary in the mean function. Now the first way you would try to attempt something like this might be, the first way I think about such things is somebody gives me a process. If they ask me to find the mean function, I say, okay, I look at the random variable, I look at this process, it's some t, then I look at the density of the distribution, I find the expectation. But when you think about this, this is quite problematic. Why? Now, what is the probability of having an arrival at a randomly chosen time instant t? Well, it is 0 because of we just discussed. So there are finite many arrivals and uncountably infinitely many points. So, but if there is an arrival, now the value of the I should be calling it the PDF. The PDF is infinite if there is, well, it's not the value of the random variable is infinite if there is an arrival. So so this is quite a problematic situation. It's not possible to evaluate the expectation with the usual classical methods. What we will do instead is we'll use a trick. So we are trying to find the expectation of z of t. So we will use the relation between z and x. So we are looking at the expectation of the derivative of x of t. This is the definition of z of t, dt. Now the trick would be to switch the places of the expectation and the derivative. Now, if you're a maths person, you should be asking me whether I have the right to do this. Can you switch the places of the expectation and the derivative? This is another issue. Unfortunately, we're in a problematic case, so it's not straightforward to do that. But let's just be, cool about it, and let's just suppose that we can do that. So this is just to let you know that these manipulations are not automatic, but in engineering we use them all the time, and it usually works. So this is d by dt of the expectation. But the expectation of the Poisson counting process is lambda t, as we just saw. So this is a nice differentiable function. So if you take the derivative with respect to t, you get lambda. So the expected number of arrivals at each time instant t is in fact lambda. So that when you look at the expected number of arrivals between 0 and t, you get lambda. So these are, if you think about it intuitively, it makes sense. But if you think about mathematically, it's crazy because there's an impulse. With 0 probability, you'll have an arrival. But then if you have an arrival, just adds infinite to the process, to z of t. So there's a kind of this 0 times infinity issue in here. But never mind, the expected number of arrivals at any time instant t is going to be lambda. So we'll just stop it there without going into further fantasy. So, all right. Now, this is good news because this matches our intuition that z of t is might be stationary. So we just showed that it's stationary in the mean. Now, again, if you think about relation to the Bernoulli processes, this is the version of the Poisson process that you might compare to a Bernoulli process. Just you can think about like 0 arrival, 0, 0. Well, I'll just draw it. If you were writing down the discrete time version of the 0 arrival here, 0, 0, 0, so then you would have 1 arrival here, 0, 0, 0, 1 arrival here. So it would be in some way related to that Bernoulli process. You see what I'm talking about? But then you have to make the time difference between two discrete values of the Bernoulli process. You should take this red length and you should shrink it to 0 in the limit to get the Poisson impulse process from a Bernoulli process. Okay, never mind about if you don't understand what I'm trying to talk about. Doesn't matter at all. So, all right. Now the next thing we have to show is it's stationary in the ACF. So Bernoulli processes are strict sense stationary, so they are stationary in the ACF. So we just commented that this thing can be seen as the limit of a Bernoulli process. So we are kind of intuitively expecting it to be stationary in the ACF. So let's just prove that fact. So the autocorrelation function of the Poisson impulse process, you see the expression in here. Let's prove this. Okay, this is again a technical proof. I'll just go through it with you, but never mind, it's quite mechanical. So Rz of T1, T2, start with the definition Z of T1 times Z of T2, but Z of T1 is the derivative of X of T. So let's just write it like this. So let's keep the second one as Z of T2. So again, if you're supposing that you can switch the places of the derivative and the expectation, you take the derivative outside, and you would be evaluating the expectation of this expression, which is the cross correlation of X and Z, evaluated at T1, T2. Now you look at the cross correlation of X and Z. So this is nothing but expectation of T1 times Z of T2. Now this time you keep the first one as constant. You write the second one, the Z as the derivative of X. Then again taking the derivative outside, this is the partial derivative of the expression X of T1 times X of T2. So you're looking at the second derivative of the autocorrelation function of X with respect to the second variable. Now, but then this is fine because we just, again, remember Z is the impulse process, X is the counting process. We just derived the ACF of the counting process. It was here. It's this expression here. So we're just taking this derivative of this expression with respect to T2. So, all right, where is it? So you differentiate with respect to T2, you get this expression. So it's again partially defined. Well, you get this is the derivative. You're differentiating this, you get this result. But then you could put it in a more compact form. So you observe that delta squared T1 is constant. So you just write as a constant term. And then there's this delta that gets added up only if T1 is larger than T2, so you write lambda times U of T1 minus T2. So this is the whole thing here is the expression for our xz. Now to find rz, we go back to here. So we take this expression and we should differentiate it with respect to T1. So this. So it means that you're differentiating this expression with respect to T1, but then, well, this one gives you lambda squared, and then you have a unit step function here, differentiated with respect to T1, you get delta of T1 minus T2. So this is, as we expected, this is a function of T1 minus T2 here, so just call it tau, you get Rz of tau is equal to lambda squared plus lambda times delta of tau. So this is the ACF of the Poisson impulse process. Now, again, we were expecting it to be stationary, intuitively thinking. Was this confirmed? Yes, this is a function of tau only, and this is why we can conclude that it's actually Z is a wide sense stationary process because its mean we found in here. Its mean is constant, and its ACF is a function of tau, the time difference. So the impulse process is stationary. Now, another interesting observation follows from here. So, okay, this is the ACF of the Poisson impulse process. Now let's find the power spectral density. So there's a constant term lambda square. So the Fourier transform of this is going to be lambda square delta f. And similarly, there's an impulse here. Its Fourier transform is going to be constant. So you get the following power spectral density for the process Z. So what's interesting here is, let's maybe just draw it. So the PSD of the impulse process, Poisson impulse process, is something that looks like this. So it has a constant term lambda, and then it has an impulse. I'll just use another color for the impulse to make it clear. So there's an impulse at f equals 0, an impulse of strength lambda square. So why is this exactly the case? Now think about it. Well, the ACF here has two components, lambda square plus lambda delta t. So this lambda square, remember that we could decompose the ACF into two terms. So the first term would be coming from the mean eta x, well, in this case, is z, so eta z magnitude square. And the second term would be the autocovariance function of the process. This is the case in here. So lambda square is the mean to the power 2 of the process. And then this is going to be the autocovariance function of the process, which tells you that the autocovariance function of the process is 0 unless you look at it at tau equals 0, which means that when you look at the process z of t at two different time instances, so look at it at some t in here and at another t plus tau in here, they are going to be uncorrelated, which totally makes sense because we know that different arrivals are independent. So whether an arrival occurs here or not is completely independent of whether an arrival occurs at another time instant or not. So it is completely reasonable that the autocovariance function of this random process is 0 everywhere except for tau equals 0. At tau equals 0, it means that you're looking at the variance of this random variable. So you get delta. So again, we're into the strange cases here. What is the variance of each the random variable you obtain by looking at z at a single time instant c? So it gets this a strange form. But how we relate this to the power spectral density is that the constant mean, so this process has non-zero mean, right? Its mean is lambda. I'm talking about z, the mean of the process is lambda. So since there is a non-zero mean, there's a constant term in the ACF, and then that term appears as an impulse at f equals 0. Remember, this was related to the DC power. We call it DC power, and total integral is the AC power, and the average power, and so on. So but then apart from that impulse at f equals 0, which is there because the process has non-zero mean, just forget about that part. The second component is flat. It's constant everywhere. So this is typical of a white noise process. The processes that have this property, we call them white noise processes. So a flat density, no variation with respect to frequency, so it's a white noise process. But this one is a white noise process that has non-zero mean. That's the only difference. If the mean of the process was 0, I would get rid of this red impulse, and here it would be just flat everywhere. Now I added a mean to the white noise process. This is why I get this impulse. So you see, there's not a single way of generating a white noise process. This is just an example of a non-zero mean white noise process in continuous time. Okay. These are all interesting observations, just putting together all the elements that we have seen so far. Now there is a question that you might ask here. So thinking about the relation between these two random processes. So you take this first one, you differentiate, you get z of t. Now similarly, you could take z of t, you could integrate, and you would get x of t. Now, we saw that z is White-Sand stationary, but x of t is not. Now, you know that integration is an LTI system, right? You could write the integration operation as the signal passing through an LTI system, as would be the impulse response u of t. So we might ask the following question: how come is it possible that I have a I'll just note here, I have a White-Sand stationary process here, and the output is not White-Sand stationary. So I'll just maybe draw it symbolically. So you have a White-Sand stationary process z of t entering an LTI system, which is an integrator. So LTI. And then the output is the Poisson counting process x of t. So this one is White-Sand stationary, but this one is not White-Sand stationary. So doesn't this contradict what we saw about LTI system? So if I have an LTI system, if I have a WSS input, the output is supposed to be White-Sand stationary. It does not, because I don't know if you have just seen the catch in here. It's because this LTI system is not a stable one. So this is not stable. So the proof that we made in an earlier chapter that WSS produces WSS at the output does not hold here. So because this is not a stable system. Well, how do you see that it's not a stable system? The impulse response of the integrator would be u of tau. And if you check the stability condition, just think about the integral from minus infinity to infinity, the absolute value of u of t is going to diverge. So it does not comply with the stability condition. Okay, so there is nothing that contradicts the theory we developed so far. Okay, similarly, you could just say the differentiator, look at the same relation the other way around. So you see the differentiator here, it takes a process that's not White-Sand stationary, but it can produce a process that's White-Sand stationary. The differentiator is stable, but there is nothing that tells you, that forbids you to have a WSS output, even though the input is not WSS. So maybe it's important to just notice here that all those conditions we derived on the input-output White-Sand stationarity relations, in all of these conditions, the stability was a sufficient condition and not a necessary condition. And just think about all of these within that perspective, maybe once more. All right, so we will conclude this chapter with an example that puts together all the properties we saw about this. This is about the Poisson counting process. It's not about the impulse process. It's a fun example, a lightweight example you might maybe enjoy without really thinking about hard theory. So this is just about modeling the number of people visiting a store. So consider a store where customers arrive according to a Poisson process of rate lambda equals 2 customers per hour. So this lambda is the rate of the process. So when lambda is given as 2 customers per hour, I know that I'm expecting 2 people arriving at my store per hour in the average. Of course, things are random. Maybe I won't have any customers at all. Maybe I will have 5 of them. But this tells me the expected number of customers. And we are interested in estimating how many customers we are likely to have and when will they arrive and so on. So let's begin with this first question. So let's find the expected number of customers that will arrive between hours t equals 0 and t equals 1. So let's maybe begin with writing down some of the observations we have made so far. So the Poisson process, the Poisson counting process we have is x of t. Think about this as a random variable. So the number of people that arrived from t equals 0 up to t, it's a Poisson random variable. We saw this, right? So this is a Poisson random variable with parameter, what was it? With parameter lambda t. And then similarly, if I'm not interested in the whole interval 0t, but I'm interested in a sub-interval, let's say between t1 and t2, We also saw that this is a Poisson random variable, and the parameter would be, this time, lambda of t2 minus t1. Well, think about this. It's perfectly reasonable to have this. As lambda increases, I expect to have more customers. So as the time interval increases, of course, I also expect to have more customers. So I multiply these two, and this is the parameter of the Poisson random variable, which is also equal to its expectation, the property of Poisson distribution. So the wider my interval is, and the higher the rate of the process is, I expect to have more customers in a given time interval. All right, so this was just a reminder. Let's now start solving the question. So the first one, what is the expected number of customers arriving between hours 0 and 1? So let's write this formally. We are interested in finding the number of customers between 0 and 1. So this is the number of customers up to time instant 1. You could also write it in the alternative way if you want. So expectation of number of people between 0 and 1. Now we just saw that this is Poisson distributed. What is the parameter of this Poisson distribution? So what is the mu of this distribution? Well, it should be equal to lambda t, but t is 1 here. So the parameter is lambda. Now, we know that for a Poisson random variable with parameter lambda, its expectation is going to be lambda. And lambda is given as 2 in the question, so we get lambda equals 2. Now, the next part. So, find the probability that at least 2 customers will arrive between hours t equals 4 and t equals 6. So, we would like to find the probability that the number of people arriving between 4 and 6 is larger than or equal to 0, at least 2 arrivals. Now, how to solve this part? Again, we use the property about the Poisson distribution. So let's just notice that this random variable is also Poisson distributed. And what is the parameter of this random variable? So if I have an interval t1, t2, its parameter is lambda times t2 minus t1. So the interval has length 2 here, so 2 lambda. So now we're in a position to calculate a probability for a Poisson distributed random variable. But then, well, we know the distribution, but to find a probability that is larger than or equal to 2, it shouldn't be 0, it shouldn't be 1, it should be 2 or higher. So if I subtract from 1 the probability that this random variable is exactly equal to 0, and also the probability that my random variable is exactly equal to 1, now I have excluded all the possibilities that make it smaller than 2. So then the next would be to just write down the probability expression. So 1 minus. So what is the probability that this random variable is equal to 0? So Poisson distribution, its mu parameter is 2 lambda. So remember the density expression. So it was exponential minus mu. So I write 2 lambda, mu to the power k. So mu is 2 lambda to the power k. I'm evaluating this at k equals 0. So to the power 0 divided by k factorial, so it's 0 factorial. So similarly, the probability is equal to 1. I write my exponential minus mu term, mu to the power 1 divided by 1 factorial. So we get this as 1 minus e to the 2 lambda. 2 lambda. Let's rewrite. E to the 2 lambda, so this term is going to be 1, this term is going to be 2 lambda, so 1 plus 2 lambda. So if you just plug in the value of lambda here, 2 times 2 plus 1 makes 5, so 1 minus 5, e to the minus power 4, e to the power minus 4. Okay, now the part C, the store opens at t equals 0, find the expected arrival time of the fourth customer. Now, this is not asking about how many customers arrived, unlike the first two parts. It's asking about the expected arrival time. So let's maybe remember what distribution is relevant to these kind of problems. So I'll just draw a realization of, maybe I'll just switch to the next page. So let's just draw a realization of the Poisson counting process. So I'm interested in seeing when the fourth customer will arrive. So I should have one arrival here, maybe another one, maybe another one, and then maybe another one in here. So this is my timeline. So first arrival, second arrival, third arrival, fourth arrival, and so on. So what is E of expectation of T4, right? This is what the question asks me to find. So we haven't derived the distribution of this random variable with what we saw so far. It's possible to do, but these are ugly expressions. But instead, what we have seen is the distribution of the inter-arrival time. So we know the distribution of x1. What was it? Remember, it was the exponential distribution, e2, E3, x2, x3, and x4. So these are exponential random variables. So the trick would be to write T4 as the sum of the first inter-arrival time and the second and the third and so on. So you're summing up from I1 to 4 the expectations of xi's. And each one of these had the exponential density. Now I just need their expectation. Remember, the expected amount of time to wait between two arrivals was equal to 1 over lambda. So this expectation is equal to 1 over lambda for each one of these. So these all have the same density, right? They all have the same, exactly the same exponential density. Their mean is all equal to 1 over lambda. So we get this as 4 over lambda, and plugging in lambda equals 2, we get this as 2. So, okay. Now, the next question is, it's a slightly modified version of the previous one. So, the store still opens at t equals 0. However, now we have the additional information that the third customer arrived at t equals 1. So, this is actually giving us some additional information about the process. We have observed the process between t equals 0 and t equals 1. The third person arrived at t equals 1. Now we're wondering when the next one, the fourth customer, is going to arrive. Now you could just modify this picture and say that this T2 is, the third arrival is known to occur at t equals 1. And now under this information of setting this time instant as equal to 1, we're wondering when T4 is expected to arrive. Now here, careful. What we will use is the independence property of all of these inter-arrival times. In a Poisson process, now, intuitively speaking, what happened within a past time interval has nothing to do with what will happen in a future time interval. The past of the process is independent of its future. This is a very characteristic property of Poisson processes. Now, under this information, if I ask you what is the expected value of T4, now you just forget about this past, and then you just take 1 and you add it up with the expected value of this random variable x4, which is just 1 over lambda as before. So the result is going to be 1 plus 1 over lambda. But let's do it more rigorously. So let's just write this as we're asked to find the expectation of T4, the fourth arrival time, given that the third arrival time is equal to 1. So the fourth arrival time can be written as T3 plus x4, right? So this is going to be T3 plus x4, now conditioning on the event that T3 is equal to 1. But then I could just plug in 1 in here, it's given. So expectation of 1 plus x4. Now I could still continue writing conditioning on T3 equals 1, but then x4 is independent of T3. So I could actually remove that conditioning. Since these are independent, conditioning on this does not add anything at all after this point on. So this is equal to 1 plus expectation of x4. But now we know that the inter-arrival time is an exponential random variable with mean 1 over lambda. So you get this as 1 plus 1 over lambda. Putting in lambda equals 2, you get 3 over 2. Okay. Now notice that the expected arrival time of the fourth customer is what we were asked in the in the last two parts, and the results are different because in the last part we conditioned this on some additional information. Actually, people arrived faster than what we predicted by knowing the average statistics. So unconditional, the fourth arrival was expected at time instant t equals 2. But now, since people arrive too fast, then this reduced to 3 over 2. You can see it in that with that kind of reasoning. Okay. Now the last part is it also goes the same. So store opened at t equals 0. The third person arrived at t equals 1. So we are still in this setting. So the third person arrived here. Now what we're asked is that what is the probability that the fifth customer arrives after t equals 2? So we can also draw a picture for this. So if you take some time instant here, let's call this t equals 2. Now we're interested in finding the probability that t5 will occur after this time instant. So t5 will be somewhere here. So how can you approach such a problem? Again, well, to deal with problems on Poisson processes, you can switch between these two interpretations. You can either use the statistics, well, the fact that the inter-arrival times are exponential, like within the last two parts, or you could switch to the Poisson distribution, telling you that the number of arrivals within two certain time instances is Poisson distributed. You can use either one, the better one that works for you. Now, in this case, I find it easier to use the number of people arriving in a certain time interval interpretation. So let's see. So the third person arrived here. We know that there's no doubt about this. For the fifth person to arrive after this, now what is the number of arrivals I should have between t equals 1 and t equals 2? So if I had no arrivals at all, now even t4 will arrive after this, so I'm fine. Now if I have one arrival, t4 will be somewhere in here like in the picture, so exactly one arrival, so t5 will be afterwards. So if I add up the probabilities of these two events, and I get the probability that t5 is larger than t equals 2. So again, let's write this formally. The probability that the fifth one arrives after time equals 2, the conditioning on the fact that the third one occurred at t equals 1, is the same as I'm looking at how many people arrived between t1 and t2. So I'm looking at this Poisson random variable. I know that this thing is a Poisson random variable. So if this Poisson random variable, the number of arrivals between 1 and 2 is equal to 0, or otherwise, if it's equal to 1, these are the only two options. If this is equal to 1, then I'm fine. t5 will occur after 2. So then the only thing we have to do is use the distribution of this Poisson random variable. Now remember again what distribution this has. This has Poisson distribution with which parameter? The parameter would be lambda times the time difference, so lambda times 2 minus 1, which is 1. So lambda. And now I just find the use the Poisson density, so exponential minus lambda, mu is equal to lambda here, so lambda to the power 0 factorial plus exponential minus lambda, lambda to the 1 factorial, so this gives you e to the minus lambda from here, and then e to the minus lambda times lambda, so 1 plus lambda, and plugging in lambda equals 2, you get 3 times exponential minus 2. So, okay, this answers the last part of the question. Alright, so to wrap it up, the thing that you should know about Poisson processes is that this counting process version is not Poisson stationary, and the essence of it's still quite interesting to look at. The thing that makes Poisson processes particularly interesting is this interplay between how the continuous random variable, exponential distributed continuous random variable interacts with this discrete time Poisson random variable. This is something that's quite interesting about Poisson processes. So it's modeled. It's used quite often for modeling things like people arriving at a store, or cars passing on a road, or photons hitting a sensor, or the data packets arriving at a router or something like that. So each one of these arrivals is corresponding to an event that's occurring independently of the others in practice when you use this for modeling things and engineering problems. So, however, this was not Poisson stationary, so we made it Poisson stationary by looking at its derivative that we called the Poisson impulse process, and this thing was related to the Bernoulli process in the limit. This can be seen as a continuous time version of the discrete time Bernoulli process. Okay, so this is all about the Poisson processes for today. So in the next lecture, we will study noise. So I hope you're all safe and you're doing well. So I'll see you in the next lecture.